Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I wanted to work through some examples which go with our unit on the chemical elements. This corresponds to chapter 11 from the Shipman, Wilson, Higgins, and/or Torres physical science text that we are using in this course. Normally here I would review the relevant equations for the chapter, but there really weren't any given at the end of the chapter right before the exercises, so we're going to have to go it alone. Well, I guess the upside is we can jump straight into the exercises. Our first example is this. Let's define the solubility is S and the temperature is T. And what we want is an equation which approximately relates S to T for potassium bromide in liquid water. Alright, you may be wondering, where would I even come up with the method for doing that? Well, the answer is that we have been given this nice figure 11.5 in the textbook, which shows the solubility, which is grams of solute which are dissolved per 100 grams worth of water, versus the temperature. And some of these are actually relatively linear or very nearly linear, or might be approximated as straight lines over some temperature range. Others maybe are more obviously curved for the entire time. In any case, potassium bromide is this green thing, which more or less looks like a line in this figure. And since it is a line, we can write for it that y equals mx plus b. And so we look at what's on the y-axis, and that's solubility. We look at what's on the x-axis, that's temperature. So in general, we can write S equals mt plus S naught. And so what we need to do here is figure out what the slope of this line is and what the solubility at temperature 0 is. That's what S naught is representing. So what we do is we take this figure, and what we're going to need to do is figure out where is S naught or S0 and what are maybe some points that are on this line from which we can get the slope. So the S0 is basically going to be where does this line end up intersecting the solubility axis. And it may be more convenient for us to pick two other points that are on the line to use as our slope points, although this one would work just fine. So in any case, I'm actually going to pick this point here and this point here. So let's see what those 2 points are. So those 2 points basically correspond to 20 degrees C gives us 67 grams of solute per 100 grams of H2O, and maybe 84 degrees C gives us 100 grams solute per 100 grams of H2O. So to get the slope, what we do is we basically take the rise over the run, so that's always delta y over delta x, and in this case what that looks like is change in solubility per change in temperature. So the change in solubilities is going to be this 100 minus this 67, so the slope is going to be basically 100 grams per 100 grams water. Strange units, I know. Minus another 67 grams per 100 grams of H2O. and then that's going to be divided by the change in temperature, which is basically 84 degrees C minus 20 degrees C. So I'm going to have to pull out a calculator now to solve this. Basically we have 100 minus 67, that's 33, and that is going to be divided by 84 minus 20, or 64 if you will. And what we get is 0.515625. So M is approximately 0.515625 grams per 100 grams of water per degree Celsius. So those are the bizarre, I will admit, looking units of our slope. So all you have to do at this point then is figure out what the y-intercept is going to be. And one way that you can do that is just look on this graph and see where is this intercepting the solubility axis. So to do that, we basically can look and see where is this actually hitting on here. And so this is 20, this is 60. So 1, 2, 3, 4, 5. So a change of 5 of these. Tick marks is equivalent to 40 here. This one is basically midway between the fourth and the fifth one. If I was going to put numbers to these, I'm not going to try because the numbers are going to be huge on this scale. But this would basically be 28, 36, 44, 52, and 60. So this is midway between maybe 52 and 60. So we'll call it 56. So basically what this means is that if I was going to try to write out an equation for this thing using the numbers that I have given, it would probably look something like this. The solubility of this potassium bromide is going to look like about, let's say, 0.52 grams of this potassium bromide per 100 grams H2O per degree Celsius. So that's our slope times the temperature of the water plus this initial 56 grams of potassium bromide per 100 grams of water. So that's basically what I would put if I was trying to write out an equation for this line. So here is that equation again. I suppose debatably you could get maybe 2 significant figures off of that chart from your book. So that's basically what the equation is. So if I was to raise the temperature to say 10 degrees C, I would have 10 times 0.52, which is 5.2 plus 56, so that would be about 61. So 10 is basically going to be this midpoint. So if I was to draw this little dashed line up to where this intersects, I see that 61 is not a bad estimate for the solubility. So that's a nice little double check of this equation that we just did. So let's see the next example. This next example says, how much of this potassium bromide can we be dissolved in 100 grams of liquid water at 50 degrees C? So now we're actually trying to use, if you want, we're using the equation that I just derived in the previous example. We could also try to use that chart to answer this question. Alright, so again, let's look at the two different methods for doing this. The first method is going to be to use that chart again. So let's pull up that chart. Basically 50 degrees C is going to be along here, so we'd have to estimate what do we get at 50 degrees Celsius. So basically you'd kind of look up along here and see where does this point right here match up horizontally, with our y-axis. If I had a method of drawing a straighter line, like say a ruler, I would maybe try that. Unfortunately, I do not have such a thing for use on this computer, but what it looks like I'm getting is maybe, so here's 60, 68, 76, 84 degrees. So that's rough estimate from sort of doing this dashed line over. Let's see, what would I get if I was going to just calculate it now. So we basically have S is approximately 0.52 grams of potassium bromide per 100 grams of water per degree Celsius times 50 degrees Celsius plus that initial value that we found of 56 grams of potassium bromide per 100 grams of water. Alright, so that's our solubility, and the question was how much can actually be dissolved in the water. So that 82 or 84 number that I found in the previous thing is the solubility. So per 100 grams, you'd have to then basically multiply that by 100 grams, and what that gives you is that you'd have 84 grams dissolved in 100 grams of water. So the total amount dissolved is going to be whatever we come up with here times really 1, because the units are per 100 grams of water. So let's see what we do come up with. So we have basically this 0.52 number times 50, and then to that we can add another 56, and we get about 82. So pretty close to what I got from the other method, 84. I think that with the chart being the way it is, with my drawing on this screen being the way it is, you have to have maybe plus or minus 5 or 4 perhaps for any estimates. So these two basically agree within that plus or minus 4. So basically we're coming up with something like solubility equals 82 grams of KBr per 100 grams of H2O, and then we're saying how much is actually dissolved in the H2O. So you're basically taking this number right here and multiplying it by 100 grams of H2O, and for lack of a better thing, we'll just call this parameter D for amount dissolved. And so you see there's a per 100 grams H2O and there's a times 100 grams H2O. And so you just end up with the amount dissolved is 82 grams of KBr, of potassium bromide, that is. So there you have it, 82 grams approximately of potassium bromide can be dissolved within 100 grams of liquid water at 50 degrees Celsius. This is again probably plus or minus 4 or so grams, so anywhere between maybe 78 grams and 86 grams would be expected at 50 degrees C in 100 grams of water. All right, what changes if we ask how much of this can be dissolved in 500 grams of liquid water at 50 degrees Celsius? Well, basically what changes here is that instead of having 100 grams here, we would have basically a 500 grams here. Everything else so far is still valid if we change the mass of the water that is being dissolved in. But this 500 grams right here, instead of calling it 500 grams, I'm actually going to break it up into being 5 times 100 grams of water. The reason why I'm doing that is because it's nice to just be able to cancel like units. So we can still cancel like this, and you have a 5 times an 82, and that's what we're basically left with. So this number times 5 gives us 408 point, gives us 410 basically. So there's some round off error, obviously. 82 times 5, 410. So in this case, we would be dissolving about 410 grams of potassium bromide. And again, there's some plus or minus in there. Actually, the plus or minus level kind of goes with this number right here. So if it's plus or minus 4 here, it's almost like saying plus or minus 20 for this one, because fractionally it should be the same as what you had here. So what that means is that anywhere from maybe 390, I'd even believe you if you said 380, all the way up to 430, and again, I'd even believe you if you said 440. Anywhere in that range, say 390 to 430 grams of potassium bromide would be dissolved. You'd have to go do this experiment yourself to get a more accurate chart. And of course, those of you who are actually taking my online lab are doing a similar experiment, but instead of using potassium bromide, you're using simple table salt, NaCl, and you're using sugar, which I don't think is on that chart. So you can kind of produce your own chart, and if you are very careful, you can actually produce a chart that is maybe nicer than the one in the book, in the sense that it's a little more precisely defined. Alright, so I think that's enough for the solubility stuff. Let's look at some other topics that are in this chapter. What's the mass of a typical hydrogen atom? So in order to answer that question, we look at our periodic table of the elements, which is actually several of the figures in this chapter. The one that we specifically want, if you're using your book to get this periodic table of the elements, is going to be the one that is actually on the cover of the book, not in the chapter itself. So if you have like the hardbound Shipman, Wilson, Higgins, and Torr's Introduction to Physical Science 14th edition book, there's a periodic table on as soon as you open the front cover. If you have one of the other editions, there's probably the same periodic table either on the front cover or the back cover. You may have to look around a little bit for it, or you can use the internet. You guys are all adults, you know how to use Google. I should say you're all taking an online class, so hopefully you know how to use Google. That's one way that you can go look this thing up. In any case, what you need from this table is that you come over to where it says hydrogen, which is this first element in the table, and it's actually this number right here. Sorry for the bad screen resolution on my screen, but this lowest number on the table in this case is the one that you want, is called the molar mass. And this molar mass actually is about 1.0079 grams per mole. And actually, if you go to the next page in the notes that I've uploaded for you, I've kind of blown one of these elements up. This one's actually helium, not hydrogen, but everything's basically in the same places. You have an atomic number, you have an atomic symbol, you have the atomic name, and then for this problem the thing you really need is the atomic mass, which again is in terms of grams per mole typically. So what we do is we use a conversion factor, which is called Avogadro's number, and that was on that last slide that I was showing you. So you can rewind if you want to look at it again, but I'm just going to write that down, Avogadro's number in this case. So Avogadro's number is about 6.0221 times 10 to the 23 atoms per mole. So this gets you, if you look at the units that we have here, we have grams per mole and we have atoms per mole. So some combination of these two should get us grams per atom. So what combination do we need to have here? Well, basically the mass is going to be, in this case, 1.008 grams per mole. And then in order to get rid of the moles, we need to have 1 mole per 6.0221 by 10 to the 23 atoms. So this, you multiply these two things together. This is basically a nice use of dimensional analysis, by the way, if you want to recall something from the first week of lectures. So we take 1.008, we divide that by 6.0221, you get 0.1673837, blah blah blah, and then there's a 10 to the minus 23 in here. Okay, so what this looks like is basically that the mass is 1.6738 times 10 to the minus, there's minus 23 here, and there was another minus 1 in the calculation, so this is minus 24 grams. And that's the same as 1.6738 times 10 to the minus 27 kilograms. Reason why I went ahead and converted this into kilograms is because if we go back and review our notes from chapter 8, that was the chapter on electricity and magnetism. So if we go back and review the notes from there, what we will find is our old friend table 8.1, which we had some reason to look at a couple of times in the last chapter's examples. And the reason why I bring up table 8.1 again is because it shows the mass of both a proton and an electron. So for a proton, 1.673 times 10 to the minus 27 kilograms. For an electron, 9.11 times 10 to the minus 31 kilograms. So this right here is basically like adding a, barely adding a 1 here. In fact, it's like adding a 9 to this place in this number. So if you were to add together an electron and a proton, you'd get basically 1.6739 times 10 to the minus 27 kilograms. So again, proton plus electron would give us 1.6739 times 10 to the minus 27 kilograms. There's a 9 here, there's an 8 here, and otherwise those two numbers are identical, which is great news because a proton and an electron, basically an electron orbiting a proton, is basically what a hydrogen atom typically consists of. Of course, you can also have what's called deuterium, where there's an additional neutron thrown in, or tritium, where there's 2 neutrons thrown into the nucleus, in which case your mass is going to be about a factor of 2 or 3 respectively higher. But those are relatively rare to simple hydrogen that has a proton and an electron. So this right here actually is in very good agreement with what we would guess just from using information from that other table. So of course, with the actual number of significant figures I was able to pull off of that table, we end up having to round to 1.674, so maybe that point gets a little bit lost. But if you find a slightly nicer periodic table of the elements, including actually the one that's on the cover of your book, then you can maybe have one more significant figure and you get to keep that 1.6738 in there. Okay, how many iron atoms are there in 1 kilogram of pure iron? And how many protons is this going to be? So to answer this, we should definitely return to our little periodic table of the elements, and we need to locate iron on there. It's actually this one right here. Fe is the atomic symbol for iron. So we're going to need this information from the periodic table, specifically how many protons are there in an iron. There's 26. And what is the atomic mass of iron? Again, sorry for the bad screen resolution. This says 55.847. So here's the iron blown up a little bit, and I should add for consistency that most sources that the atomic mass is actually 55.845. I think there is actually some discrepancy in the 2 editions of the textbook on that point. So I'm going to go ahead, actually, because when I originally worked this example I had the textbook that gave me this number in front of me. I'm going to go ahead and work it with this number, and it's not really going to differ substantially from this one. Alright, so what we can do, for example, is say that the mass of an individual iron atom is given by the molar mass, which often is represented by a big M, divided by Avogadro's number, just like what we did with the hydrogen in the previous example. So this is basically saying 55.847 grams per mole. And then we're going to divide that by 6.0221 times 10 to the 23 atoms per mole. Alright, so let's pull out our calculator and see what we see here. So we have 55.847. We're going to divide that by 6.0221. So 9.27367 times 10 to the minus 23. So it looks like we can write that the mass of a single iron atom is approximately 9.2736, and maybe we'll keep the last digit but round off because it's actually 3675, so we'll round that off there, times 10 to the minus 23 grams per atom. Right, and the question was how many atoms therefore are there in a kilogram? Well, I guess this means we should probably convert this into kilograms, so there's 1,000 grams in a kilogram, so that means that this is equal to 9.27368 times 10 to the minus 26 kilograms per atom. Alright, so to get the number, we now have basically the mass of a single atom of iron. And this is basically going to be like an average mass. In fact, there are different isotopes of iron. That means that many of them, they all will have the same number of protons, 26 protons, but some will have one number of neutrons and some will have another number of neutrons and so on. So that's actually also going to account for why is there a difference in different sources' answer for what's the molar mass, is they're accounting for different isotope ratios. In any case, if I wanted to find the total number of atoms in a given mass, then I would use basically the total mass in question and divide it by the mass of a single iron atom. So I'm going to label this MFE for mass of iron. And so this is basically going to be, we had 1.00 kilogram, and then we're dividing this by 9.27368 times 10 to the minus 26 kilograms per atom. So that's kind of a mouthful to say. So whip out that calculator. Basically we do a 1 over x thing. So you get this number times 10 to the minus 26, divided by 10 to the minus 26, which is the same as times 10 to the plus 26. So this number basically is 1.07873, and that can be times 10 to the 25 atoms. Every atom of iron has the same number of protons, 26, and that's true regardless of which isotope of iron it is. So if we want to find how many protons there are, we use that the number of protons is basically the number of atoms times the number of protons per atom. So that's the little n. So we would have 1.07873 times 10 to the 25 atoms, and that's times 26 protons per atom. So what we need here is to pull out our calculator. 1.07873 times 26 gives us 28.04. So 28.04698, and that is now going to be times 10 to the 26th because I've moved the decimal place over one here. And so that's how many protons we have. And so collectively these two numbers form the answer to the question asked, which how many iron atoms and how many protons are there in 1 kilogram of pure iron. So if we round off, because we only had 3 significant figures of mass to work with, that's going to be 1.08 times 10 to the 25 iron atoms and 2.80 times 10 to the 26 protons. Okay, so we can measure the density of copper. That is, as you recall from chapter 1, that is going to be the mass per unit volume. So the typical density of copper is 8.96 grams per cubic centimeter at room temperature. So the question is, suppose we're given a big chunk of copper, 0.450 cubic meters of pure copper. How many copper atoms do we have in that? It's a pretty big chunk of copper, by the way. That's approaching the size of a desk made of solid copper. And by desk, I mean, imagine a block of copper that was solid all the way through that's about the size of a small school desk. Alright, so we're going to ultimately need to go to the periodic table and find copper. It's number 29 on the periodic table, and we need to know what is the atomic mass. You probably can't read it because of the screen resolution, but that's 63.546 grams per mole. I'm going to go ahead and put it a little larger on my little workspace screen so that you can actually see that number, 63.546 grams per mole. So we will come back to that number in just a minute, because first of all, we've been given that the density is 8.96 times, 8.96 grams per cubic centimeter. And the volume that we've been given is 0.450 cubic meters. So we basically either need to convert this into grams per cubic meter or convert this into cubic centimeters. It really doesn't matter which of those two things you do. I'm going to go ahead and convert this number into grams per cubic meter because that's actually a conversion factor that a lot of you guys have had trouble doing. So this is kind of a nice review of the first chapter just before we finish the class out. So let's look at that. So rho is equal to 8.96 grams per centimeter cubed, and that's the same thing as basically saying grams per centimeter by centimeter by centimeter. So what we need to do is multiply this by the number of centimeters per meter, and we need to do that for the number of dimensions that we have here. So we basically have to do that 3 times to eliminate all 3 of these centimeters down here. So centimeters, centimeters, centimeters gets rid of centimeters, centimeters, and centimeters. So we need to do 8.96 times 100 times 100 times 100. You can do this quickly with scientific notation because 100 is 10 squared, and so we have 10 squared cubed, so that's 10 to the 2 times 3, or 10 to the 6th power. So we can just write that out as that the density of copper is therefore 8.96 times 10 to the 6th grams per cubic meter. For what it's worth, if you wanted to figure out the kilograms per cubic meter, you would then convert grams to kilograms by basically dividing this number by 1,000, and so you'd have 8,960 kilograms per cubic meter. But we don't really need to do that because our number down here is in grams per mole, so leaving it in grams per cubic meter is helpful to us. All right. This basically gets us what the density is. The next step is to figure out how much total mass must be in this volume. So that's part of why I converted this over into grams per cubic meter, because in general the density is defined as the mass per unit volume, and the thing that we're given here is a mass per mole. So what we're looking for is the mass of copper that is in this given volume. So to do that, we would have mass is equal to density times volume. So that's going to be 8.96 times 10 to the 6th grams per meter cubed times 0.450 meters cubed. So let's see what we have when we do that multiplication. 8.96 times 0.450 is 4.032. And then we need to include that times 10 to the 6th. So the total mass that we actually have is 4.032 times 10 to the 6th grams. All right, at this point, the problem is now quite similar to the problem that I worked in the last set, which was, how many iron atoms are there in 2 kilograms, or excuse me, in 1 kilogram of pure iron. So at this point, we have a mass of pure copper, and we just want to know how many atoms there are. So the way that we do that is basically that we say that the number of atoms is going to be equal to the total mass, which is what we just found here. So basically the total mass divided by the mass of a single copper. And what that's going to be equal to is the total mass divided by the basically the molar mass over the number of atoms in 1 mole. So in other words, in A, M divided by Na, where this number right here represents M. So this is M for Cu, copper that is. So all of this basically becomes the total mass times the Avogadro's number divided by the molar mass. Okay, let's plug our numbers all in here. So the total mass is 4.032 times 10 to the 6th grams. We're going to multiply that by 6.0221 times 10 to the 23rd atoms per mole. Going to divide that by 63.546 grams per mole. You could get that, by the way, by just doing dimensional analysis, because what we're going to see here is we have a per mole here and we have a per mole here. We have a grams here and we have a grams here, and so we're left with the unit of atoms. So the number of copper atoms can be found now by using the calculator. So we have this guy times 6.0221, and then we can divide that by 63.546, and so we get 0.3821. So let's write that here. This is approximately 0.3821 times, we have 10 to the 6 here, we have 10 to the 23 here, so this is 10 to the 29 atoms. And to make it a little more proper in scientific notation, we'd move this here and we'd subtract 1 from up here, so you get that the number of copper atoms is approximately 3.821 times 10 to the 28 atoms. And that is our answer. That's how many atoms do you have in 0.450 cubic meters of copper, of pure copper that is. And of course, with significant figures, that becomes 3.82 times 10 to the 28 atoms. So that's quite a few atoms, but that's also quite a lot of copper. All right, next question is, how much energy do we need to singly ionize 2 moles worth of hydrogen? So we're basically moving along now to the part of the notes in which we talk about ionization energy. So to answer this part, or this example, you're going to actually want to look at basically this figure, which is not the entire periodic table, obviously, but it is figure 11.24 from the Shipman physical science text, and we're talking about helium, so we're actually looking at this particular part of the figure. What this is basically telling us is that helium has a single ionization energy of 2,372 kilojoules per mole. And the reason why I specify that it has a single ionization is that there are actually 2 electrons in helium, just like there's 1 in hydrogen. So if I wanted to ionize helium, all I have to do is remove 1 of those electrons, and this is how much energy per mole it would require to remove an average of 1 electron per atom, per helium atom that is, for 1 whole mole of helium. If I wanted to remove a second electron and totally ionize the helium, I would actually need a much larger number than this, because I'd have to ionize that second helium electron. And in fact, the ionization energy for that second is not just another 2,372, because it takes more energy to bring the second electron off than it does the first. It takes more to bring the third off than the second in the case of lithium, and so on. So the ionization energy is basically going to be given by the number of moles times the molar ionization energy. So the number of moles we might represent as Nm, and that's going to be times the molar ionization energy. So if we had 2 moles times 2,372 kilojoules per mole. So let's see what we get for that. Oops. 2 times 2,372 gives us 4,744. So 4,744 kilojoules per mole, or if you'd like, 4,744,000 joules. Shouldn't be per mole because I've actually eliminated the moles here. So this per mole is, oops. So this is the total energy needed to ionize 2 moles worth of helium by removing 1 electron from each helium atom on average. So that seems like quite a bit of energy, and maybe it's worthwhile to compare that to let's say a kilowatt hour, which is the unit by which energy is delivered to houses. So remember that a kilowatt hour was 3,600,000 joules, or 3,600 kilojoules. So this is actually only slightly more than a kilowatt hour, like maybe 1 1/3 or so kilowatt hours worth of energy. So our next example is slightly more difficult than that last one, but it's sort of a follow-up of sorts. The question is, how much energy is required to singly ionize an oxygen atom? Alright, so to do this, we're going to need to go back to table 11.24. So here's table 11.24 from your Shipman, Wilson, Higgins, and Torres 14th edition physical science text. And we need to find the oxygen on this table, so that would be O. So this right here is the molar ionization energy, 1314 kilojoules per mole. Alright, and then we wanted to know for a single atom, so we're probably going to need to have that conversion factor from moles to atoms. So there are 6.0221 atoms, 6.0221 times 10 to the 23rd atoms per mole. Alright, so simple dimensional analysis can be used here again to get the equation that's needed. So the energy in this case is going to be whatever combination of these two we can do to eliminate moles and end up with joules and atoms. So the ionization energy per atom is going to be 1314 kilojoules per mole divided by 6.0221 times 10 to the 23 atoms per mole. So there's a per mole here, there's a per mole there. We're left with kilojoules per atom. So let's do our little calculation. That's 1314 divided by 6.0221. You end up with 218.19 or whatever. So this is 218.2 kilojoules divided by 10 to the 23 atoms. So if I wanted to move this thing over a couple, that's going to change this number by 2. And so I end up with an energy in this case of about 2.182 times 10 to the minus 21 kilojoules per atom. So that is the ionization energy for oxygen, and of course you could also convert this into joules per atom, which you do then by essentially by multiplying by 10 to the 3 joules per kilojoule. And so you end up eliminating the kilojoules, and this thing you have to add a 3 to. And so that ends up being 2.182 times 10 to the minus 18 joules per atom. And in fact, that's also the correct number of significant figures, given that we had 4 significant figures to work with when we looked it up on the periodic table of ionization energies. Okay, let's take it up one more level. This is sort of the most difficult level of thing that we would do with these ionization energies. The molar mass of neon is about 20.2 grams per mole. So how much energy is needed to singly ionize 3.00 kilograms of neon? So this problem, other than the fact that we were kind of given what the atomic mass of neon is, this problem actually could be utilizing 2 different of these tables. So here's that periodic table again, and you'd look on here to get the molar mass of neon, and 20.180, and so that was rounded to 20.2. Then you look on this other table, the figure 11.24 from your text, and it gives the ionization energy in terms of kilojoules per mole for neon. So 2081 kilojoules per mole. All right, but the question here was ultimately how much energy do we need to singly ionize 3 kilograms of neon? So I'll represent that as E for 3 Ne, just for shorthand. And this is what our question mark is. Well, what we need to do here is basically convert this from grams per mole to kilograms per mole, so that then we can multiply this number and this number, well, really actually divide this number by this number in order to get the ionization energy. So in general, the ionization energy is going to be, by unit analysis, once again, the ionization per mole divided by the molar mass. So that basically looks like 2081 kilojoules per mole divided by 20.2 grams per mole. But we got to remember to convert this into kilograms, because we also end up having 3 kilograms. So we actually maybe need to multiply this by the mass. So this is 1 kilogram is 1,000 grams, and then we have 3 kilograms worth of stuff. So this right here is basically the ionization energy per kilogram. So this is ionization energy per kilogram. And then this right here is the mass in kilograms. We could, for example, have decided instead to leave this one alone as just the not convert this into kilograms, and instead converted this guy into grams, and we'd get the same answer. So let's look at our units. We have per mole and per mole. We have grams and we have grams. So this grams and this grams cancels. And then we have kilograms here and we have kilograms here. So unit-wise, this all works out. So our energy is going to look like this. Let's pull off our calculator, plug these guys in. 2081 kilojoules times 3 kilograms divided by 20.2 over 1,000, because this one's over 1,000 here. And the answer we get is 309,000. So we basically just got 309,059 kilojoules. Okay, so that's scientific notation wise, that might be 3.09059 times 10 to the 5th kilojoules, and then we can multiply that by 1,000 joules per kilojoule if we so desire, and so we would end up with a total ionization energy for 3 kilograms of neon singly ionized 3.09059 times 10 to the 8 joules. So either of these would work fine as the answer. And of course we actually only had 3 significant figures, not because we were limited here. Of course we could easily go look this one up and get a few more significant figures. Again, this was 20.180, so I could have had 2 more sig figs here, But 3.00 kilograms of neon gives us 3 significant figures, and that means that we would need to round to 3.09 times 10 to the 8 joules. And that's how much energy you would need to singly ionize 3 kilograms of neon. That's actually quite a lot of neon though, so this would be a pretty huge sign if this was using 3 kilograms worth of neon. It really would light up the city if this was so much neon being ionized like this. Well, that's all the examples for this chapter, for this unit, for this lecture, whatever you want to call it. So I hope that you found these videos helpful. And really, I hope that you found all of these videos where I've worked through these examples helpful. Those of you who are in my physical science class will almost certainly not be continuing with me in any further classes, since physical science is sort of a standalone single semester class, and very rarely does a student take that and then end up taking a physics class later on, because this is usually taken by the non-majors to fulfill some requirement in their general ed, and usually people don't switch from, say, communications into bio. So in a sense, this is like the last video that you would normally watch from me, outside of maybe any kind of question that you have in the last week of the course online. So really, I hope that you've found all these videos that I've made helpful. I've poured many hours into making these, obviously, not just in the sense that each of these videos is about an hour, but in the sense that it often takes me a couple hours to record and maybe another hour or so to edit any given 1 hour video. So I really hope that you guys have gained something from this, from watching all these videos, and that you do indeed appreciate them and that they are helping you to learn. So I suppose this is farewell.